Now I am going to discuss this problem. A zero order homogeneous gas reaction A2RR, that is whose stoichiometric uh, coefficient R is not known, proceeds in a constant volume bomb. What do you mean by bomb? That is a closed vessel. So if there is a volume increase, then there will be pressure also increase. So with 20% inerts and the pressure rises from 1 to 1.3 atmosphere in 2 minutes. So seeing the pressure variation, it would be possible to find out the kinetics. So first part of this problem is kinetic analysis. Second part is reactor design. So using the first part of the problem, you can find out the rate constant. The next part, if the same reaction takes place in a constant pressure batch reactor, what is the fractional volume change in 4 minutes? You see, initial part was constant volume bomb and second part constant pressure batch. What is the difference of this? Because second part we can observe the volume change and the first part we can observe the pressure change. In the level scale book you will find some various types of problem where first part is either zero order, first order, second order, any type using a constant volume bomb in order to find out the rate constant, and secondly that data you have to use for finding the reactor design. If it is plug flow reactor, then we can find out the volume of plug flow reactor. But here it is batch reactor, so you can find out the volume change, or you can find out the time required if volume change is specified. Say the volume increase is given twice. So we know V2 will be 2V1. It is given. We can find out the what is time requirement. So second part may be any type. So only one problem I am discussing in the class, and other problems you can go through the book, exercise of 11th school, or I'll give in the form of assignment. Solution: zero order reaction, and initially added 20 moles inerts, so 80 moles is A, and after reaction 80 moles of R will form and 0.2 moles inerts remain same. So what is delta N? Delta N is R minus 1 from the reaction stoichiometry, R minus 1. So what is A? A is here 1. That's why it is R minus 1. And for constant volume reactor, pressure rises. Write the equation in the form of total pressure as discussed in the theory part. Write the mole balance in terms of partial pressure, that is dividing Pa by RT. Integrate, you will get the equation 1 by RT Pa minus Pa naught is equal to KT. Then this is the equation where we can substitute Pa or Pa minus Pa0 in terms of total pressure. It is partial pressure of A. And fortunately here one reactant is present. So this partial pressure sometime may be total pressure also. But still you can use this relationship. That is relation between partial pressure and total pressure that I have discussed in some previous classes. And A by delta N, it is known. A is 1, delta N already we found delta N is R minus 1. So substitute R minus 1 in the equation and pi minus pi 0, that is total pressure at T is equal to T and total pressure at T is equal to 0 time, different total pressure. And substitute this in the equation of PA minus PA naught. So next line you will get A by R minus 1 RT pi minus pi 0 is KT. From here time is given 2 minutes, substitute 2 minutes, substitute total pressure 30% rise of total pressure, that is 1 to 1.3, and substitute 1.3 minus 1 and getting the relationship between K and R, small r, and capital R gas constant is known, and temperature this should be given. Here in this problem temperature is not mentioned, so write in terms of T and K, it is unknown. So next part, constant pressure batch, that is variable volume reactor, and apply the theory of variable volume reaction. Design equation is why variable volume, because as per the stoichiometry A is giving RR, not 1 mole of A producing 1 mole of R mole of R is producing. So apply the stoichiometry and you will observe there is a volume change with reaction. Then design equation for variable volume reactor, batch reactor is in the integrated form T is equal to Ca naught 0 to Xa in terms of Xa, obviously in terms of conversion. Then go through the integral 0 to Xa, integrating 0 to Xa, you are getting Ca0 by epsilon ln 1 plus epsilon Xa Kt. Then Ca0 by epsilon A ln V by V0. So in this expression V by V0 we can find out. If we know K and K we can substitute, and before that what is the stoichiometry here, it is different. In the problem second part it is different, not 20% inert, 40% inerts, and pressure is also different, 3 atmosphere constant. This is constant pressure batch reactor, so it is maintained at 3 atmosphere. So there will be volume change. Because this is variable volume, so there will be volume change. Stoichiometry 0.6A, 0.4 inerts, 0.6 R, and 0.4 inerts. 0.6 R means small r times of 60%. Initially supplied 0.6, so it is 0.6 times R. Capital R will form. So 0.6 R minus 1 by 1, it is epsilon. Substitute epsilon in the equation, above equation, Ca0 by epsilon ln V by V naught is Kt. Substitute Pa0. Pa0 is 60% of total pressure is 3, so Pa0 is 1.8. So Ca0, it is 1.8 by RT. So substitute 1.8 by RT, 0.6 R minus 1 as per the equation, epsilon 0.6 R minus 1, and Kt, K again substituted 0.15 by R minus RT. You observe RT times smaller minus 1 get cancelled from both sides. So only ln V by V naught is remaining. Ln V by V naught is 0.15 by 3 into 4, 0.2. So it is a typical problem. If I do not describe it, it is difficult to solve. So now you can solve it. V by V0 is 1.221, so 22% volume rise, 22.1%. And fractional volume change is 0.221. This is the answer. Sure. I am starting again from flow reactor mole balances. Two types of mole balances. See, for CSTR or mixed reactor, we are having the mole balance in the form of this Fa0 1 minus Xa0, Fa0 1 minus Xa. So up to this, most probably I have shown in the previous class. Then from here you are getting the mole balance in two different forms. Either you can write V by Fa naught, just 1 minute. I'll use the pointer and describe it. This is the one type of mole balance. V by Fa0 is equal to Xa by minus Ra. So if we have the rate expression, we can substitute rate expression, and for a note it down, that is, if the rate equation is given in the form of known rate parameters, that is K, that is first order, second order, or complicated rate model, if it is supplied, then we can use it for reactor design. So what will be the input parameter? Rate constant, order of the reaction, conversion, and feed rate. So for any specific capacity of CSTR or mixed reactor, we can design for volume of the reactor using this equation. And mind that it is for isothermal only. So for isothermal reactor design, in case of mixed reactor, we can use this equation encircled with red color. And if it is in terms of concentration, say final concentration is specified, CAF, then use the equation V by Fa0 is equal to Ca0 minus CAF, that is this part. Second term we can use. And if the rate kinetics is not known, then volume must be given. And you see, for kinetic study, we can perform in a known reactor size, say 1 liter reactor or 1.5 liter, 2 liters, whose volume is known. So in mixed reactor of known volume, if we perform the reaction, and if we know either final concentration CAF or Xa, we can use it for kinetic study. So the same mole balance, it has two applications, either for kinetic study and secondly or for reactor design. And reactor design means finding volume, that is volume will be the output, and for kinetic study second part, rate constant will be the calculated parameter, and first part for reactor design, volume will be the calculated parameter. And what is the input parameter for reactor design? Full form of rate kinetics and other concentration, Ca0, Ca, etc. Achha. The equation also can be written in the general form, tau is equal to in Ca0 minus Ca by minus Ra, or in this form. And what is tau? Tau is the space time, and this is also called design equation for finding reactor volume. Inside tau, volume is there, and what is tau? Tau is volume and volumetric flow rate ratio. So if we have V by V naught, V by V naught, that is, if tau is specified, means volume and V naught, then we can use for kinetic study. And if only V naught is specified and rate constant is given, we can find for V. So this is also design parameter, tau. And why it is written in terms of tau? We are getting two equations. Tau is equal to VCA0 by FA0 is equal to CA0 minus CA. And in terms of conversion, this. So if we plot it, this already I have discussed, still I am repeating because this is the main part of reactor design. Two types of plots you can use for reactor design. Either you can plot reaction rate minus RA in terms of conversion or concentration. Here it is shown in terms of concentration only. And or we can plot reciprocal of rate, that is minus 1 by RA. Plotting in terms of concentration. So you'll get this type of curve. So this is 1 and this is 2. You remember these two types of curve. And first type of curve, it is used for finding operating condition. So if tau is specified, okay, tau is specified and initial concentration is known and the rate equation is also we can plot. If it is say rate equation is minus RA. Giving example 1.3, this is rate constant, and Ca to the power 1 by 3. So what is rate equation? 1.3 Ca to the power 1/3 fractional order. We can plot it, and this plot is given here. So this is the rate versus Ca plot. And Ca is varying from Ca0 to 0, 0 in the origin for x is equal to 0. And you see, if we use one CSTR of size 1 liter, volumetric flow rate, say 200 milliliter per minute. So we can find out tau if volumetric flow rate V naught and size of the reactor is known, tau is known, then you find out 1 by tau, draw the line starting from Ca0, draw the straight line starting from Ca0 and it will cut at a point on the rate curve. This will give you final concentration. Say this is the first reactor, reactor 1, and if this incomplete conversion or unconverted steam CAF, if it is added to second reactor with the same size and same volumetric flow rate, that is two reactors are connected in series, then we can draw the same straight line, means same slope with minus 1 by tau, minus 1 by tau. And we can find out the second reactor outlet concentration. Now, you will learn from this, if we have the rate kinetics, we can plot the rate equation in terms of concentration and draw the line starting with Ca0 with a slope 1 by space time of the first reactor. Achha, now mind that always the reactor size may not be the same. So if first reactor it is tau 1, second reactor may be tau 2, then the slope will be different. And third reactor it may be another slope, say tau 3. And in this way we can reach to up to a 0 level conversion. That is very small conversion. Why it is used in series? Say one reactor is not sufficient to attain the final conversion. So if we have 3 reactors in series, we can go up to this Ca3. This is Ca3. And this is Ca2. Just I am explaining this in paint. This laptop is becoming slow now. It will take time. Slide. Not coming. Okay, leave it. I am drawing here. Say this is first reactor. This is second reactor. This is third reactor. Is it visible? These three? These three reactors? Yes or no?
Yes, sir.
So if three reactors are connected in series and feed is added in the first reactor with a concentration Ca0, then effluent from the first reactor it is added to the second reactor, effluent from the second reactor is added to the third reactor, and it is called CSTRs in series model. And in CSTR in series model we can go by this method, plotting rate as a function of Ca. So it is enough. I think it is clear. Achha, if the reactor size are different, then the slope will be different. We can draw the straight line with different slope with 1 by tau 1, 1 by tau 2, 1 by tau 3 to reach the final concentration. So we can solve for Ca. And otherwise the alternative method is you write the mole balances for three separate mole balances for three reactors, reactor 1, reactor 2, reactor 3, three mole balances, and solve these three equations to get Ca3. And what is the application of the second plot? Second plot is only for finding reactor volume. First plot, their reactor volume is specified, it is known. But second plot, reactor volume is unknown. Then you find out the rectangular area of the rectangle CAF, CA0 joining with CA0 and CAF, that is size of the base of the rectangle is CA0 minus CAF, CA0 minus CAF. If you go through the equation, you will find that is 1 by minus RA multiplied by CA0 minus CAF is equal to area or tau. So using this equation, we can find out the area of the curve, area of the rectangle, and locate the final concentration on the rate curve, that is reciprocal of rate curve here, final concentration, and draw the rectangle passing through this point only. If the final concentration is here, then the size of the rectangle will be very large, like this. So same, it is in terms of conversion. Here also it is plotted starting with conversion. 0 means from origin and final conversion is XA. Locate the final conversion in the in the exit of the CSTR. In case of CSTR, always after attaining steady state, inside the CSTR, whatever the conversion, that will be same as the outlet conversion. And XA, it is the steady state conversion after attaining steady state. And calculate area. Area is tau by Ca0 or V by Fa0. If Fa0 is known to you, you can calculate size of the reactor. And variable volume reaction, only use the expression for V0 multiplied by 1 plus epsilon XA, and both the volume will be corrected, V0 multiplied by this term and small v0 multiplied by this term, and the right hand side will be this. So KT is becoming this equation. This is for variable volume first order reaction. And this is a function of XA. This can be plotted as a function of tau. to get rate constant. This also I have shown. I am repeating this. Rate equation is minus RA C square. Second order kinetics. Then one more term will be extra here because it is square. So 1 plus epsilon x square will be there. Square. Then this is the design equation for second order. And if k is known, we can find out tau. And if tau is known, we can find out k. So the same mole balance can be used either for kinetic study in order to find out rate constant. Secondly, in order to find out tau for finding reactor volume. Plug flow reactor, already it is described in some earlier classes. The plug flow mole balance is given by minus dFA by dV minus RA. So this is the differential form of mole balance. Achha. Now this rate may be any type. You have started heterogeneous part, heterogeneous reactions. So the rate models can be given like this: K1 multiplied by PA minus PR PS. This will be in the numerator and denominator will be 1 plus Ka PA PR like this, so on. So in the denominator, there will be some adsorption terms. These Ka, Pa, Kr, Pr, these are called the adsorption parameters, adsorption terms. This is dimensionless. So Pa is in terms of atmosphere or Pascal, any pressure unit. So this will be pressure inverse. That is the unit of adsorption equilibrium constant. This is adsorption equilibrium constant. This is adsorption equilibrium constant for R. And if the reaction is A2 R plus S. This type of reaction, the rate model is given by this. So the integration is difficult. We cannot find out the integration. So this rate equation directly we can substitute here. Okay, this rate equation we can substitute directly here. But it is a function of A on function of partial pressure terms, PA, PR, PS, etc. Then how do you solve it? Then this FA we can write in terms of partial pressure, or this FA we can write in terms of conversion, and all PA, PR, PS can be converted the conversion functions of the respective partial pressure terms. So if we write the conversion terms, conversion functions, then it can be solved using Runge-Kutta method. This will be first order differential equation whose initial conditions are known. We can solve it using a program. That is, you can write a mathematical program using any method, or directly you can solve it using MATLAB, Excel, etc. And if the rate kinetics is not so complicated, it is first order, second order, then you substitute rate equation in terms of conversion and integrate it. And the example is given in terms of conversion only. Design of plug flow reactor where all expressions are written in terms of conversion. Fa is written in terms of conversion like this: Fa naught 1 minus Xa, and Fa0 dxa by dv is written minus Ra, মাছ করে না হট করে রোজ যাওয়াটা কোন দিন ভয় লাগে তো। And V by Fa naught we can write tau by Ca naught. In terms of catalyst weight, we can write minus dFA by dW is equal to minus Ra prime. This is another design equation for heterogeneous reactions, solid catalytic reaction. Then the rate expression is written Ra prime in per kg basis. Substitute rate expression if available in the form of Langmuir-Hinshelwood kinetics, as I have shown in the last slide. Minus Ra, K is the rate constant, partial pressure difference term, and the adsorption terms in the denominator. So this rate equation we can substitute here and solve it. In the first equation, this is equation 1, differential form, and this is equation 2, it is integral form. So integral form, if integration is possible, we can go through it, otherwise you use it using differential form, and analytical solution is possible by using Rangakutta method. And here it is explained graphically. If minus 1 by Ra is known, we can plot it. It is Ra known, so it can be used for reactor design, PFR design, isothermal obviously. So for isothermal plug flow reactor design, plot minus 1 by Ra in terms of conversion and find out the area under the curve up to final conversion. দুধ এসছে দাঁড়িয়ে থাকুন দাঁড়ান and for first order kinetics using plug flow reactor, here rate constant multiplied by Ca, this is written in terms of variable volume concentration term. So 1 plus epsilon A Xa will be in the numerator. Then after integration you will get two terms, 0 to Xa dxa by 1 plus minus Xa plus epsilon A 0 to Xa, Xa by 1 minus Xa dxa. And after integration we obtain k tau is equal to 1 plus epsilon A ln 1 minus Xa minus epsilon A Xa. This is entirely function of Xa. So we can start with Xa is equal to 0 and give some increment 0.1, 0.2 like this, and you go up to the final conversion. So evaluate this function for various conversion level and plot in terms of tau. In terms of tau. So if conversion versus tau data is available, you can solve it. And constant volume process epsilon is 0, so the equation is very simple, and this is function. This is function of Xa. And variable density for second order kinetics, and we are getting equation after substituting K Ca0 square to the mole balance in the form of variable density xa1 plus epsilon a x square by k ca0 square 1 minus x square. In terms of xa, you can integrate. After integration, this big equation, complicated equation is available. Here you can substitute conversion again and evaluate this quantity and plot in terms of tau to find out the slope ca0 k. This. So the previous equation k tau minus 1 plus epsilon a ln 1 minus xa minus epsilon xa, it is used for first order kinetics and this is used for second order kinetics. Now second order kinetics will study some cases. Some case studies are there so that this will be clear what is the effect of epsilon on the reaction rate. And right, tau is equal to AC. AC is the cross section area of the reactor. L is the reactor length. So this is volume. And V0 is volumetric flow rate. Substitute here. Then write in terms of length of the reactor. Length as a function of conversion. So this is another form of integrated form. So reactor length, how this will vary with conversion and epsilon, we can observe here. Let us choose the parameters. Rate constant is this 5. Cross section area is 1 decimeter cube. Concentration initial is 0.2 mole per decimeter cube. And volumetric flow rate is 1 decimeter cube per second. And so this group, this parameter V0 by CA0 K AC is becoming 1. And within bracket it is dimensionless. It is dimensionless. What is the unit of this? This is length. V0 by CA0 K AC, it is having unit of L, length. Now, case 1, we can study here with increase of epsilon, what is the effect? And it is plotted, this equation is plotted with various epsilon, that is epsilon minus 0.5 to 2, minus 0.5012. And it is possible if the stoichiometry A to B by 2, A to B, A to 2B, A to 3B, various stoichiometry of the equations. And it is epsilon varying, that is increases if you go downward. So what is the case 1? With increase of epsilon, with constant conversion, length will increase. So the first point for same conversion here, length, and this is L2, this is L3, and this is L4. So gradually L will increase if we change the stoichiometric ratio or stoichiometric equation. And second case, keeping reactor length constant means using the same reactor if we perform different reaction with epsilon different, then conversion decreases as epsilon increases. That is, you will come down with a constant length means you will follow in this path. That is constant conversion, you will follow this path, and constant length you will follow this path. So if epsilon gradually increases, reactor length keeping constant, conversion will also decrease. So conversion decreases. With increase in epsilon, conversion decreases. And here with increasing epsilon, reactor length increases. Reverse. And this effect of volume change is also explained with this plot. Let us consider the reaction A to 2B plus C. with epsilon a 2. Now if we neglect 2, that is epsilon is 0, we'll get one plot. This is plot 1 and this is plot 2 for epsilon 2. So for epsilon 0, top 1 and the below, that is with epsilon 2. Here we can compare with the same way. Acha. Say neglecting volume change, epsilon is 0, L1 is the length. And the conversion is 60% here. L1 is the length, conversion 60%. But if you correctly account this with the same length, conversion will be 40%. Acha. However, correctly accounting the volume change is 2, then the length required L2 will be. So using L1 as length, we will get less conversion. XAV is 0.4. That is explained by using the vertical downward line. That is vertically you have to come downward to reach epsilon is equal to 2 curve. So various curve if you draw for various epsilon, we can compare the addition of inerts, effect of inerts. That is third point. If we add 50% A with 50% nitrogen, then YA0 is 0.5 and what is epsilon A? 2 into 0.5 is equal to 1. So epsilon is 1. So this will reside in between 0 to 2. That is somewhere in between these two curves. Difficult to draw this. That this is for epsilon is equal to 1. So if you add inert, epsilon will decrease from 2 to 1. Addition of inert, epsilon will decrease from 2 to 1. And what is the effect on that? That is 2 to 1. If epsilon decreases, conversion will increase. So for any reaction, if you add inert for having high epsilon, then epsilon can be decreased. And with decreasing epsilon, we can increase better conversion, right? So this is the application for industry. Why we use inert? Inert we can use in order to increase the conversion level, or we can reduce the heat effect. By diluting with nitrogen, we can dilute the heat of reaction, total heat of reaction, and ultimately it can be maintained at low temperature. That is, overheating can be avoided. Damn-Coehler number in this equation, K Ca0, K tau in this mole balance, K tau Ca0, this group, it is called Damn-Coehler number for flow reactor, second order kinetics. And this tau, if it is replaced by small t, this will be same as for batch reactor. So for batch reactor, first order kinetics, Damn-Coehler number is Kt, and for plug flow reactor or mixed flow reactor, this will be K tau. And Damn-Coehler number for nth order reaction, this will be Ca0 n minus 1 K T or tau, either small t or tau for flow reactors, and all are dimensionless groups. So you have to remember this. I'll show one more slide. Just start, but cannot be completed now. Different problems for flow reactors. These are very, very important to solve the problems for CSTR and plug flow reactor. One CSTR, one or two problems already I have described. This is a problem of variable volume. Constant pressure but variable volume reaction. Volume increases twice. A to 2B is the stoichiometry. So the problem statement is homogeneous gas reaction A to 2B is run at 100 degrees centigrade at a constant pressure 1 atmosphere in an experimental batch reactor. The data obtained with pure A. What size of plug flow reactor operated at 100 degrees centigrade and 10 atmosphere would yield 80% conversion and 90% conversion of A for a total feed rate of 10 mole per second. The feed contain 40% inerts. So the problem you have to read twice, thrice. What are the data given? Data given: temperature, pressure, flow rate, final conversion, then percentage inerts, flow rate, that is mole per second, means molar flow rate, FA0, for a total feed rate of 10 mole per second. Total means including inert, total feed rate. And at different time, V by V naught is supplied. Assume a first order kinetics. Now, this problem I'll go to the next class better. Today I have discussed the theory part, and few plug flow reactor problem will be discussed in the next class. So better you can ask if you have any queries or questions. If you don't have any question, then I can leave.
Thank you, sir.